In this example, we're going to be maximizing profit. So we're given some information about this company. This company sells Q ribbon winders per year at P dollars per ribbon winder. All right, then we're given a demand function for the ribbon winders. Remember, demand simply connects together price and quantity. So P is price, Q is quantity. Ribbon winders cost $30 a piece to manufacture. Plus there's a fixed cost of $9,000 per year. We want to figure out what quantity we should be charging where profit is going to get maximized. So we want to maximize our profit. So let's go ahead and try to come up with a couple different functions. Let's come up with a revenue function. Okay, revenue is going to be given by, that's all the money you bring in. So whatever you charge for these, the price, multiplied by however many you're selling, we can call that the quantity. All right, so we can be charging P, and we're going to be selling Q, right? Price times quantity. A lot of times we're going to use R for revenue is equal to P times Q. So in our case, what we want to do is we're given that the demand function. So let's use that demand function and fill in for P with 300 minus 0.02 Q and leave Q for our quantity. All right, now our function R is all in terms of a single variable. All right, so if we expanded this out slightly, we would get 300Q minus 0.02Q squared. All right, so we have a revenue function. And then the next thing I'm going to go ahead and do is create a cost function. So cost is going to be given by any of the variable costs plus any of the fixed costs. All right, so our cost function in this case, let's think about it. For each ribbon winder we sell, it's going to cost us $30 to manufacture. So that's going to be $30 multiplied by however many we sell. All right, so however many we're going to sell is going to be our quantity Q. Next, we have fixed costs, and they tell us we have fixed costs of $9,000 per year, so $9,000 is going to get filled in there. So now we have this nice function for our cost. Now we have a couple different options to go about maximizing profit, and I'm going to show you both of them. All right, we can compute profit is going to be all the money we bring in, the revenue, minus all of our costs. All right, kind of makes sense, right? Profit is what's above and beyond the money you bring in minus everything you have to pay out. So R minus C is one way to treat this. So the profit function could be given by 300 Q minus 0.02 Q squared, right? Just filled in for my R, minus, and then we're going to subtract away 30Q plus 9,000. But a big set of parentheses around that. Now why I want to do the big set of parentheses around that is that negative, that subtracting away, needs to be distributed. So minus 30Q minus 9,000. So our profit function is going to be given by, combine some like terms here, maybe we put the negative 0.02 Q squared out in front, plus 270 Q minus 9,000, combining those like terms with Q to the first power. All right, so two different ways we can solve this. We've created a profit function. One way to go about this is find the derivative of the profit function. Okay, the derivative here is going to be using the power rule. We go negative 0.04 Q to the first plus 270. Next, we want to find critical values or critical numbers by setting this equal to 0 and solving down. So I'm going to subtract that 270, move it to the other side, and then divide both sides by the negative 0.04. This will give us an ideal value. Our quantity is going to be 6,750 items. All right, and that should maximize our profit. Now we can double check to make sure it actually does maximize our profit by doing the second derivative test, by calculating the second derivative. So power rule from the first derivative, negative 0.04, which is negative, and that's important that this indicates that our graph is concave down. everywhere, actually, not specific to that specific value for Q. So if it's concave down everywhere, that's going to indicate that we get a maximum at this value of Q. That's the first way to find our ideal quantity. The other way is slightly different. Remember, we already computed the revenue function. We can figure out what is the marginal revenue, which is going to be the same thing as the derivative of the revenue function, which would be 300 minus 0.04 Q. And then we can go over to our cost function and we can find the marginal cost, which is the same thing as the derivative of the cost function, which would be 30. And our maximum profit is going to occur whenever the marginal revenue is equal to the marginal cost. All right, this will maximize our profit. Okay, so we've done the computations. That's going to be 300 minus 0.04 Q. We're going to set it equal to 30 and then work on solving this down. So we can subtract that 300, move it to the other side. And you're going to notice we get negative 270. We're going to divide both sides by negative 0.04. Get Q on one side by itself, and guess what we get to? We get to 6,750 for our quantity, just like we did the other way. Now, this has its limitations, that if you do it this way, as I did on the right-hand side, we don't really have a profit function that we created, but it does cut out some of the other steps, right? So like doing that second derivative test just to double check and make sure that this is concave down at that quantity. You can't really do it this way, but we usually don't run into any real big problems. It does save a little bit of time as opposed to making the profit function and then finding the quantity. However, if you needed to find what would the profit be, remember what you would do is you would take the value we just found, doing it the second way, and you could plug it back into our revenue function and into our cost function and find that difference by subtracting them pretty quickly, and you can get the maximum revenue. All right, hope this helps out. Good luck.